Hello, everyone. My name is Alex Taran, and I'm software engineer in Rusolut company. And today I would like to show you new things that we implement in Visual Nand Reconstructor 5.1 update. In this update, as always, we have added some new XOR keys for Phison devices, for microSD and SD cards, as well as new ACC-BCH algorithms for devices and new chip configurations and trial algorithms. These algorithms and configurations partially added with help of our partners. Special thanks for this addition to our technical partner, Arvika Data Company. As well, as usual, we have added new pinouts in our pinout database, so new devices could be easily read and data recovery from them. There are some microSD cards, SD cards, and monolithic devices. As well, some of these devices are provided by our partners and customers and clients too. So if you receive some new case and some new device which is absent in our database, feel free to make some request support, and we will help you with this device and search pinout for this. Let's move to the main topic about this update. Some devices based on Phison controllers, Phison and Sandisk controllers are used some kind of rotation principle. It means that data stored inside the block, then this data is rewrite into another block or into another place, is updated by adding new data on top of old data. That means you could see here that original NAND block contains some data in the page. When controller wants to add some new data inside this block, the controller copies this data from original block to buffer, and then add into the buffer new data on top of currently existing data. And this makes some data shifting inside the buffer, and this shifted data put it back into the NAND. So into the NAND, we have mixed pages order and mixed data order. And to revert these things, new block rotation element was invented. This element has really simple interface, only two options: block rotation type and marker position. Block rotation type has 5 possible variants to choose: 2 for Phison controllers and 3 for Sandisk controllers. And marker position points to the exact marker position, rotation marker position, and this option fills automatically once you have choose correct rotation type for your case. For Phison, correctly chosen, it's Phison, and Sandisk. So the next question, how to determine if rotation and block rotation is used by controller and required to be reverted by block rotation element and Visual Nand Reconstructor. When you have some files, maybe covered, maybe even file system correctly restored from device, but these images, these files looks like they combined from different images, different parts of images, then most probably there are some rotation was used by controller in this case. So you could see here file system, even file system recovered, and some files are green, some files are bad errors, and here some example file which consists of parts of different images, and that's how looks block rotation after finding it in the case. Let's see how it's possible to determine additionally to check if block rotation is actually used or not. Here on this slide, you could see a standard Phison service area. It looks like vertical stripes. These stripes is absolutely clear and easily seen inside one block. From block to block, these stripes are different, but inside the block between pages, these service areas are exactly the same. In this case, in Phison controller, when we have such stripes, vertical lines, there is no any rotation for Sandisk controller. As I said, Sandisk has two types of rotation. Here is example of static block rotation. Static block rotation could be determined by FF marker on 4th byte of service area, and visually it could be recognized by some stripes, not periodic or partially filled stripes in service area. Also, it could be some dot pattern in case pair element should be used previously before block rotation. Service area is our 4th byte, and rotation marker contains located in 6th and 7th byte of service area. As this static block rotation, we have for every rotated block our rotation marker inside the first block of inside the first page of every block. And these patterns could be easily recognized visually inside the DOM just looking into the service area. As Phison dynamic rotation, simply slightly different from static rotation, because rotation marker could be located anywhere inside the block if block was rotated. But every such rotation marker marked previously by header, and here header is 83. So this 83 header located in 4th byte of service area, and we could recognize it by vertical lines inside the block. These lines is full of 83's values, or short horizontal lines, single headers. When you have this long line as header in marker, we could see some counter pattern. You may recognize it on this image. As well, we may determine by these short lines and determine if this rotation is used for Sandisk for Phison controllers. As for Sandisk, there are no header for these controllers. They use only rotation markers, but Sandisk, every Sandisk which uses rotation puts these rotation markers on the very first pages of block with rotation. So we could determine it by 4th and 5th byte of SA. If block contains markers for rotation, they will look something like this, like short vertical lines, non-periodic, non-continuous inside the block. And these markers contains only information about rotation applied. So some additional calculations performed by block rotation element are made to reverse its rotation and eliminate it. For Sandisk rotation, we have 3 different types. These types named as rotation Sandisk by 2 pages, by 4 pages, and by 8 pages. What does it mean? This Sandisk works with some kind of virtual pages, and rotation applied on this virtual page level. On physical level, we have in this example 8832 bytes per 1 page, but we have single pair element with number of planes too. This element will increase virtual page size twice, so result page size will be twice bigger. And in this case, for this exact example, we should use Sandisk 2 pages rotation to eliminate the rotation applied on this controller to this case. Next example is Sandisk 4 pages block rotation. Here we could see slightly different situation. Block size, page size 90-16 bytes per single page, but here we have 2 pair elements, single pair and second pair, and for each pair element we have number of planes too. So first pair element with 2 planes, second pair element with 2 planes, it will be by multiplication provide result as 4 times bigger virtual page will be than physical page. In this exact case, we use Sandisk 4 pages rotation for this exact example. And final rotation type for Sandisk for the moment is 8 pages rotation. So for beginning, we have 66 4 bytes for block size and have two pair elements. First pair element with 2 planes and second pair element with 4 planes. 2 multiplied by 4 will provide result as 8. 8 times bigger Sandisk virtual page will be bigger than physical page from Nand itself. And that is why we should use here option with Sandisk 8 pages rotation. I could remind that after selecting correct page, correct rotation type, marker position will be set automatically. For Phison, this one values, for Sandisk is another values. So for now, let me show you how it works on real cases, how it proceeds, and how the things going. Here you could see some case about Phison dynamic rotation. This case is a quite standard one. We have 2 physical image reading from reader, applied ECC correction, applied XOR key, and pair elements per one dump, each for one dump. And then with unite element, we connect these dumps together to get the results. As for now, without any rotation, we have result like that. Let me show you what we have. File system detection takes a little bit time because in this case without rotation, applied file system isn't correctly read. So we could say file system tries to be recognized, but files absolutely corrupted, so file system isn't correctly working, even file system isn't working. If we check some ECC, we may see that here all is all green, no problem inside ECC correction, so it could not be binded with ECC errors or some problems with chip reading. And how could we determine inside the dump? How could we prove that we have some bit block rotation inside this element? Just open dump, navigate to service area, and search for results. What's inside service area? For standard Sandisk, for standard Phison controllers, we have service area at byte 1025 till byte 1031. And here, if I highlight blocks, we could visually see some non-periodic patterns. And here, the exact example which I show you on the slide, we have here some headers, 83, here at 83, 83FF, and the rotation marker. In this exact case, 4138. So we may observe that there are many such blocks with some kind of markers. Not every block may have such rotation, because rotation caused by how controller writes data into the NAND. If you will write data sequentially one by one file, rotation will not be applied by controller during the writing to the NAND. But if you will copy files not sequentially, but maybe in several threads, it will be caused, it will make rotation on NAND writing. So we determined that this exact case required rotation to be applied. And now let me add this element just after unite element, and let's look how it will work. Just add it like this, connected to the markers table, select correct rotation type. Here is with Phison dynamic rotation, and you even not required to recreate markers table and recreate logical image, because rotation are made inside block, so block ordering isn't changing. And now if we reopen file system, we could see that results is much better than previously was. Here are some pictures, and they're showing correctly and working properly. Let me show again how it works without rotation and how it works with rotation. Exact same elements, just copying them and connect directly after unite element to compare the results, how it was before and how it works after. I have to open some markers table, preload it, and create logical image. So here we could see that page filter is still activated for this case, and we have no rotation. And the results for file system and files looking like this. Here we have our file system, even could find correct folder on the root, but files inside this file system are totally corrupted, even with page filter correctly applied. So that is how rotation works inside Phison controllers. Let me show the example how it works inside Sandisk, how it finds, how to determine, and to use this element inside Sandisk. Here we have exact same case, really simple Sandisk case, just one physical image, ECC applied, XOR key applied, and pair element with 2 lanes. Number of lanes is 2 here. So I have extracted some part of this case to speed up process, because there are many corrupted images inside. Just for showing how it works, I think it will be enough. Let's build logical image and look inside this offsets with file carrier. You could see that here we have some images, but all of them are bit error, only one good image, and most of them are with bit error or even critical image. And here is our images. Just write images just from example I showed previously. You could see here we have mostly normally images, but they combine it out of parts of different images. And this thing, in most cases, shows us, tells us that we should use block rotation element in this case. So let's add this element just right here. Pair element. Add this block rotation after pair and connect it to logical image and markers table. Let's recreate markers table and scans exact same offset with exact same file color. Here, wait, I forgot, completely forgot. I forgot about to set correct option. Without correct option, block rotation will not work by default. Thanks, Summer Beer. By default, when you put block rotation element on the workspace, it will not affect any dump, any byte, any bit inside the dump. It will just pass the data through this element without any modifications. But here we have single pair element with 2 planes, and we know that this case is Sandisk rotation. We may look inside the dump and see service area of Sandisk, standard Sandisk service area here. Let me find and show how rotation markers looks like inside Sandisk exactly. There are not many blocks in this case with rotation, and it could be difficult to find exact place where rotation marker exists. Oh. Here it is the place when we have exact rotation marker. Fourth and 5 byte. This and this 2 bytes is our rotation marker. So we have found that Sandisk and uses rotation by 2 pages. Let's correctly configure this rotation. After you choose rotation type, correct marker positions are set automatically. And now just open offsets and make some carver. And for now, results is slightly better, much better. We have many good images from exact same offset, from the exact same place of the dump. Images are perfectly recognized and perfectly restored without any errors, without any mixing and ordering. So only 2 options: block rotation type and markers, and second option sets automatically. So this element is pretty simple to use, and you get results as fast as possible without any additional calculations, without any steps. Just apply and you will be good. The next thing that I could talk about and discuss and explain is a parametric concatenate element. This element is an update of our standard concatenate element, but now with help of this element it's possible to concatenate a few dumps of different sizes with some parameters, with some rules. These rules are written in area sizes field by numbers. For example, we have here 3 different dumps for different images. Let's assume we have really small dumps. First dump 6 bytes, second dump 2 bytes, and third dump out of 4 bytes. And we would like to concatenate them with some periodic rule to have 3 bytes from first dump, single byte from second dump, and 2 bytes from third dump, and so on till the end of every dump. This element will allow you to do that perform. Just connect all 3 dumps into the 3 inputs and set rule 3, 1, 2. What these numbers mean? It means the number of bytes to take from every input accordingly. So this element will take 3 bytes from first input, single byte from second input, and then 2 bytes from third input, and put it group by group. You could see here 3 bytes from first input, 1 byte from second input, and 2 bytes from third input. And then after 1 cycle of this concatenate will be done, element will continue till the end of source dump. So you will receive 1 single dump concatenated by this rule and these parameters. How could this thing could be used for case recovering and data files recovering? Some Phison controllers, for some reasons, uses such kind of block rearrangement. they divide dump in group of 4 blocks. 3 blocks go in sequentially: block 1, block 2, block 3, and then 4 blocks consist of 3 little parts of addition of this block. So here we have first part, big part of block 1, and here in 4th block we have last part of this first block, and so on. Second block and second part of this block, third block and second part of this third block. To rearrange them correctly, to get correct images, correct dumps, correct files out of recovery process, we require to reverse this thing. So to eliminate this rearrangement made by block, we require to divide dumps into 2 parts. One part will contain only big parts, so 3 out of 4 blocks will go into the part 1, and second part will contain every 4th block out of 3 blocks of dump. And then after divide, we could use concatenate element to join all these dumps into the single image. How it will work and what parameters should be used for that. As input, part 1 and part 2 should be applied as a rule: the size of this block as first number and size of this smaller block as second number. So the concatenate element will take number of bytes of this block, big block, and put into the result dump. Then from second input, it will take this small block size number of bytes and put it right after this big block, and so on till the end of the dump. So it will provide us correct physical, and after that logical image of the dump without any rearrangement. And this thing will provide possibility to recover data, because without this possibility, even you have correct maybe file system, because file system may not be affected by this rearrangement, files could be corrupted or even not could be recognized absolutely. And let me show some example when this principle is working and how it looks, how it works, and explain a little bit. Here we have some Phison case, quite standard Phison case, but this case, besides block rotation, uses this rearrangement as well. Very standard beginning: physical images, ECC correction, XOR, pair, unite by dumps here, and after that use block rotation. Block rotation here in this case is static block rotation, nothing special, just put it into the workspace, set correct options, and it will work. After block rotation, we make some markers table to get correct arrangement of the blocks, and after that the magic begins. Here in this exact case that I told you before, we have 2 different types of data processing by controllers. Controller would not affect by rearrangement blocks with file system. So controller rearrange only blocks that starting from some point of the dump. So here we extract some offsets only file system block, several first blocks of the dump, and this offset takes the rest of the dump. And here, without this element and rearrangement, we may just connect it together like they was and try to see logical image. Here, file system isn't affected by rearrangement, and we could even correctly here see some files, even some folders, but if we go inside folder, we will see some garbage. There is no recoverable options and no recoverable files here. But if we connect our element after this rearrangement and recreate refresh logical image, the results will be much better. Here, exact same file system structure, and here we could correctly see every image in every folder absolutely working without any issues, without any problems. So just few clicks and you will have from corrupted, unrecoverable file system and files fully working file system. It's really amazing thing in this update. So let me show step by step in details with some explanation and parameters. Here we have some offsets, data blocks with data, with files, and two offsets. As I said before, first offset takes first 3 blocks of every 4th block group, and second offset takes that last 4th block of group of 4 blocks. And concatenate element join these dumps in sequential order. It takes one block, big block from here, this dump, and little block here from this dump. And you could see this size, this number, area size is exact same as we have our block size. So this one and this one same. And second number is 3 times smaller because this block, this offset contains parts of the blocks which we should concatenate to every block on the dump. And after concatenation, we will join all these dumps together and get correct logical image. Just simple, little bit calculations to define correct numbers, and you will receive correct working file system. So that's all for today. Thank you for your time and see you on next update videos. Bye.